not give to us in their cases equal to m r squared alpha. If this is a I and this is a I, and from the previous example, we already know that alphas of I for each article, each particle, each mass point have the same angular association. So the total tau equal to summation of tau I equal to 1 to n, then that is equal to summation of m I, in that case is equal to m I r I squared times alpha. So ladies and gentlemen, that is equal to I alpha. So now we find another rotation and linear motion. What we studied before for the linear motion, in the linear motion, we have force equal to ma. A is in linear motion, it's called acceleration. Now rotation motion, very nicely though, we have what we call tau is equal to I over alpha. How nice. So if you look at this, m is equivalent to moment of inertia. I equivalent to the angular motion, angular association. So all the things is a pair. So what is next? What is quality of angular motion? In linear motion, there's a quality of motion. It's called momentum. So that has something much equivalent to momentum. So in this, in the linear motion, we have F is equal to time rate of changing of momentum. So now we like to ask ourselves, if that is the case, tau equal time rate or changing of what? Okay, so this is that makes the study of physics or study of anything is kind of what they call the story to tell. Story to tell. So we have tau is equal to I alpha, angular momentum. So from the base there, the first one, the rotation, we know tau is equal to I times alpha. So now you'll be playing the same game we've been playing with the force, because our force is equal to ma last time. Force equal to ma. So we say if force equal to ma for the linear motion, we have F equal to ma that equal to m dv dt. Remember that? And then after that we have d mv dt. And then we define that mv is called what? Called momentum. So for observation we say that the force is equal to time rate change or momentum. So now we're using the same game to do it. So torque is equal to I times alpha, as a section 10.7 to tell us. Then why don't we do this? I equal to d omega dt. And then we have another one is d I times omega dt. look, here is a tau. So tau is equal to d dt I omega. Bingo, we got it. So the quantity of rotation is turned out equal to I times omega. So m I v omega. So this one is related with momentum, but it is related with rotation. Anything related to rotation, we give a name called angular momentum. So this is dl dt. Okay, so all of a sudden that we define that in the logic. So in linear, in the rotation, what we have? So again, is on the 10.6, 10.8, 10.8 angular momentum. In these cases, it's called L. So in the linear motion, we have linear rotation. In linear, we have force equal to momentum. In rotation, where tau are equal to time rate change of angular momentum. So in the linear motion, we have when there's no force adding on the collision, no force adding on the isolated system. So what will that happen if there's if F is equal to 0, then d dt p equal to 0. So p is equal to constant. When there's no force adding on a system that has conservation on linear momentum, because p is constant. Okay, now if there's no torque adding onto the system that equals 0, then d dt L equals 0. So L is equal to constant. That is called what? They're called conservation of angular momentum. That is equal to I omega. That's what Marcel Quant take the advantage of this angular conservation angular momentum. When it stretches out and we rotate, then when it stretches out, because the R is larger, so moment of inertia is larger. So the angular speed is smaller. When it stretches back, then the R is smaller. Moment of inertia of angular momentum, then the angular velocity increase extremely fast. That is called conservation of angular momentum. And we have to have a very detailed description about this conservation of angular momentum. We highly suggest that you're using that to do the special project on. Chapter 10 is finished, and 10.11 we did the lab. 10.11 we did the lab. And you can 10.15 the development there is one of the potential examination problem. Now for you to do this, we'd like to give you some more hints. Number 76 is very good. 76, 73 is very good. 73 is good. 76, 73. There's another one is number 59. It's good. Now, and then 54. Okay. Okay. Now there's a homework. I already mentioned the example. 10.15 is good. And
54 and 76 evens.
54. Yeah, that's an even number.
Yeah.
Yeah. Now there's one problem, like a 59. Is almost equivalent problem, like in the example. The example is example 10.5. That means if you know how to do the example 10.5, you should know how to do the number 59.